Welcome to this explainer. Look, if you're managing complex engineering projects, your absolute number one concern is probably mitigating risk. And a huge part of that comes down to predicting exactly how your materials are going to perform out on the worksite. Are they going to hold up under stress? Will they melt, shatter, bend? Well, to answer those big macro-scale questions, we actually have to understand the micro-scale reality. So today, we're bridging that gap. We're going to look at the very foundation of the materials you specify and procure every single day.
Here's a quick roadmap for today's briefing. We'll start by defining material structure scale, compare crystalline and amorphous solids, decode the unit cell, navigate Miller indices, look at engineering crystal structures, and finally apply this to real-world materials. All right, let's jump right into Section 1, defining material structure scale, from atoms all the way to infrastructure. As a project manager, you're evaluating material spec sheets all the time, right? But let me ask you this. What exactly defines the internal structure of the engineering materials you're relying on? On an atomic level, structure is simply the organization of atoms relative to each other. But that simple organization, it dictates virtually everything about a material's success on your job site. Okay, let's dive into this. What we're looking at here is the structure properties performance tetrahedron. Notice how atomic structure is sitting right up there at the top node. That atomic structure directly dictates the properties of the material, how it can be processed, and ultimately its performance in your specific applications. Characterization sits right in the middle as the method we use to analyze these relationships. Long story short, if you want to predict performance, you have to start with structure. To really wrap our heads around this, we gotta adjust our sense of scale. Over on the right side, we have the macro scale. You know, the worlds you manage. City traffic at 10 to the 5th meters, road infrastructure, heavy vehicles. But the structure of a material operates way down on the left side. We're looking at atomic structure, short and long-range atomic arrangements, down to 10 to the negative 10 meters for an atomic lattice. That atomic lattice is to your materials what a massive structural steel frame is to a skyscraper. Which brings us to Section 2, crystalline versus amorphous solids, the fundamental divide. So the absolutely crucial point here is how atoms organize themselves when they solidify. We basically have two main camps. First, crystalline solids. These feature regular, ordered arrays of components. They exhibit periodic, geometrical arrangements over large atomic distances, which is what we call long-range order. On the flip side, we have amorphous solids. These completely lack a systematic and regular arrangement. In fact, they're sometimes called supercooled liquids because their chaotic atomic structure literally resembles a liquid, possessing only short-range order. And this really brilliantly illustrates that physical difference. Check out the amorphous solid on the left. It's just a randomized, messy web. Now compare that to the crystalline solid on the right, with its highly structured, repeating, and entirely predictable geometric pattern. And keep in mind, within crystal materials, you can have single crystals, where the pattern is perfectly continuous, or polycrystal materials, shown on the far right, where multiple crystalline grains interlock like a giant puzzle. To connect this right back to the procurement sheets you handle every day, when you specify metals, alloys, or advanced ceramics, you are banking on the predictable strength of crystalline or polycrystalline materials. But when you're sourcing inorganic glasses or flexible polymers like polycarbonate, you're relying on the chaotic flexibility of amorphous materials. Moving on to Section 3, we are decoding the unit cell, the ultimate building block. Since crystalline solids are basically repetitive 3D patterns, it's super helpful to break them down into their smallest repeating chunk. That's the unit cell. It's kind of like a single brick in a massive wall. It is the basic structural unit that defines the entire crystal structure by virtue of its specific geometry and where the atoms are positioned inside it. Make no mistake, this is the foundational metric scientists use to engineer materials. Now, what's really interesting about this is the sheer variety of these building blocks. Depending on the length of their edges and the angles between them, there are 7 distinct crystal systems. We've got everything from the perfect symmetry of the cubic system to the elongated tetragonal, the hexagonal, all the way down to the completely asymmetrical triclinic. Every single crystalline engineering material you use is built from billions of these specific shapes stacked together. But what's actually holding all these blocks together? Well, the atomic bonds. And this maps perfectly to the material classes you select for your projects. Metallic bonds, where freely wandering electrons form a sort of sea around the ions, give us our metals and alloys. Ionic and covalent bonds combined give us our hard, rigid ceramics, and a mix of covalent bonds and much weaker van der Waals forces gives us our flexible polymers. Simply put, the bond type dictates the material class. All right, Section 4. Let's navigate Miller indices, essentially the standard operating procedure for mapping this stuff.
Our source defines Miller indices as a shorthand notation to describe certain crystallographic directions and planes. Now, why on earth does this matter to you as a project manager? Because by studying these coordinates, directions, and planes within a unit cell, material scientists gain the exact insights needed to design entirely new materials with custom-tailored characteristics for your high-stakes applications. It is literally the language of custom material design. Think of calculating these Miller indices for directions as a strict standard operating procedure. First up, you determine the coordinates of 2 points lying on your direction of interest. Next, subtract the starting coordinates from your destination. Then, you just clear any fractions to get your lowest integer values, and finally, lock those indices safely inside square brackets.
Let's actually see this logic play out on a standard cubic unit cell. To find the Miller index for direction A, we take the endpoint coordinates, 1, 0, 0, and we subtract the origin, 0, 0, 0. That leaves us with 1, 0, 0. There are no fractions to clear here, so we just bracket it up as 1, 0, 0. This standardized coordinate system allows engineers worldwide to communicate exactly how a crystal is going to behave under stress, along very specific internal lines.
Let's step back a bit for Section 5, common engineering crystal structures like FCC, BCC, and HCP. Let's see how this geometry actually builds the heavy-duty metals you're specifying daily. Face-centered cubic, or FCC, gives us ductile metals like aluminum and copper. Body-centered cubic, or BCC, forms high-strength metals like iron and tungsten. And hexagonal close-packed, or HCP, yields metals like zinc and titanium. The internal geometry directly, and I mean directly, defines your metal's capability on the job. And finally, Section 6, real-world engineering materials, looking at polymers in practice. Polymers are a fantastic example of how structure dictates performance, especially when we talk about heat resistance. You've got linear and branched polymers, which consist of long chains held together by relatively weak van der Waals forces. Because those bonds are weak, they're easy to break with heat, meaning these materials will melt or soften pretty easily. But if you look at cross-linked or network polymers, they are tied together via strong covalent bonds. These complex three-dimensional linkages are nearly impossible to soften, making them thermosetting polymers. If your project environment involves high heat, this structural difference is literally the line between success and total failure. So we've traveled all the way from macro-scale infrastructure right down to the atomic lattices, unit cells, and the bonds that hold the whole shebang together. Understanding whether a material is crystalline or amorphous, how it's bonded, and what its crystal structure looks like, that isn't just theory. It's your ultimate tool for risk mitigation. So I'll leave you with this to chew on. How will these atomic-level structural insights reshape the material choices and risk assessments on your very next engineering project? Thanks so much for joining this explainer.